Good day. Today I want to talk a little bit about organic synthesis, and in particular how we do retrosynthetic analysis. I want to look at problem 38 from chapter 11 and letters B and C from that. What you see we have here is two hexane diols, and they happen to be diastereomers to each other. Both problems ask you to make these hexane diols from propyne. So the first thing I notice is that I'm going to have to make a carbon-carbon bond here because I start from a 3-carbon unit and I want a 6-carbon product. You haven't learned very many ways to make a carbon-carbon bond. As a matter of fact, I think the only way you've learned so far is from a terminal alkyne, making an acetylide out of that, so making this carbon and nucleophile, and then reacting that with an alkyl halide to get us a longer alkyne. That could get us a chain pretty easily. But how about our diols? We have 2 OHs on there. What are ways we know to put a diol on a system? And remember, the 2 products we want are diastereomers. This one would have resulted from an anti-addition of 2 OH groups across the cis 2-hexene. This would have been from a syn addition across 2-hexene. One of the ways we know to make a diol is with osmium tetroxide and T-butyl peroxide. This results in a syn addition of our OH, so would probably work quite well with our right-handed product, but not so well with our left-handed product. On the other hand, we can take our alkene and with a perbenzoic acid, most commonly metachloryl perbenzoic acid, we can make an epoxide. And although we haven't covered the chemistry of epoxides in this class, you did learn about them when you learned about SN2. So an epoxide is a pretty reactive compound. We can come in with a strong base such as sodium hydroxide, and it does an SN2 reaction, which means it's undergoing inversion, or in this case, it's going to react to give us an anti-addition of our product. So that would work really quite well with our left-handed product. So what would our total synthesis look like? Again, we've got a 3-carbon alkyne we're starting with. We want to get to a 6-carbon unit. So the first thing we're going to do is activate our propyne by pulling off that hydrogen with sodium amide to give us propyl acetylide. And then we're going to react that with propyl bromide to give us our 6-carbon 2-hexyne. If we reduce that 2-hexyne to cis 2-hexene using Lindlar's catalyst, we get to a good background for what we have. We have a CH3, a carbon with a hydrogen off of it, another carbon with a hydrogen off of it, and a propyl group. And we have a reactive center here in our alkene that will allow us to add our diol. If we want to add our diols syn to each other, we're going to use osmium tetroxide and T-butyl peroxide, and that's going to give us product C here. If we want to add the 2 OH groups anti to each other, we're going to have to do a little fancy dancing. We're going to make an epoxide first and then do an SN2 reaction in ring opening that epoxide. So we're going to use metachloryl perbenzoic acid, and we're going to use hydroxide. So what did I do? The first thing I did in this problem was I figured out, do I have to make a carbon-carbon bond? And I did. The second thing I needed to figure out is how could I make my functional groups? I knew I was going to have a triple bond. I knew I needed diol in my system. Well, the way I knew to make diols were from an alkene. I can make an alkene from an alkyne. So what I'm thinking about is chain elongation, converting our alkyne to an alkene, converting our alkene to a diol. And then I'm paying attention to the stereochemistry about whether I want my OHs to add syn or I want my OHs to add anti. Thanks for listening.